Hello, my name is Jeff Squires. I work for Cisco Systems and I'm one of the developers on the Open MPI project. This screencast is about the OpenFabrics protocols that Open MPI uses in the version 1.2 series. The protocols that we use can be broken down into basically two parts: what happens with short messages and what happens with long messages. So let's talk about short messages first. For short messages, if you recall from an earlier screencast, the registering memory is a fairly expensive operation, so we try to avoid that as much as possible. One of the tricks that we do is we pre-register a whole set of buffers during initial connection setup, so that when you have a short message come in, we can just mem copy into one of those pre-registered buffers and send from there. Now, we define a short message as the cost of mem copy doesn't matter. So it's small enough that the mem copy is irrelevant in terms of the overall send and receive time. Now, once that message is copied in, we do one of two things. We either use RDMA to send the message, or we use send-receive semantics. Now, let's look at this pictorially in terms of the pre-registered buffers. So I've got an MPI send here, and it's some short message. So let's say it's 8, 16, 32, or 100 bytes or something like that in a user buffer there on the left in the blue. Now on the right, as I mentioned, there's a whole queue of pre-registered buffers. So when you do the send, Open MPI will dequeue one of these pre-registered buffers and mem copy your message into there. And it has to be obviously less than or equal to the size of our pre-registered buffers. And then we'll either use send or RDMA semantics to actually transmit the message across the wire. And we'll talk about that a little bit more in a minute. And when we're done, we'll return the pre-registered buffer to the queue so that it can be used again by some future short message. Now let's compare RDMA semantics to send-receive semantics. So RDMA semantics, the sender has to specify the buffer address on the receiver. So if you think about that, a sender has to do all of it has to figure out exactly where it's going to put this message in the remote process's memory, which means there had to be some kind of coordination beforehand. The receiver said, here's a bunch of addresses that you can put messages into. Now, it also requires some pre-registered buffers on each receiver for each sender. That's an important point right there, that multiple senders cannot share a single RDMA receive message buffer, because how could a single sender know if some other sender has already written into that address? There's no good high-performance way to know that, so the only way you can do it is to really have registered buffers for each sender. And you can see how this quickly becomes non-scalable for short messages. The other way is to use send-receive semantics, and this is where the receiver specifies the target buffer where messages are given. And a common technique there is you just have a whole pool of pre-registered buffers, and you say, hey, network, whenever a message comes in, put it in one of these buffers and then let me know about it. So let's look at this pictorially here. On the left, RDMA shows that I've got a peer A and a couple of messages being sent there, and a peer B and a couple of messages being sent there, and they're both being sent to a common receiver. And the receiver has had to set up a bunch of buffers ahead of time and give all those addresses to A and B and say, here's where you can RDMA messages to. So we had to do this initial setup of exchange of addresses. But the nice thing about it is that it's completely hardware driven. It doesn't involve the main CPU. It doesn't involve the software stack or anything. Once you initiate the transfer, the rest of it happens completely hardware driven and asynchronously, which is a very nice property. Now, what happens though when you have more messages than you have available receive buffers? So you can see on the left here, peer A has 4 messages to send, but only 3 messages, 3 receive buffers in which to send. So what happens here? Well, Open MPI on the sender has to do its own flow control and realize that there are 3 messages outstanding. It has to wait for the message 1 to be consumed by the receiver, and once that happens, then message 4 can go back into that original buffer there. So Open MPI has to do its own round robining of the buffers and acknowledgments and things like that. Now on the send-receive side, it's a little bit better and a little bit worse and a little bit more complicated. There's less initial setup. We don't have to do this exchange of addresses thing that RDMA has to do, but the driver picks the buffer. So if you look, the picture is a little bit different here. I still have peer A and peer B, and they're both sending 2 messages each, but there's a common pool of buffers. And so the network driver and the network hardware do the picking of which message goes into which buffer. It's usually a FIFO kind of thing, but we can't rely on, Open MPI can't rely on anything. The networking stack puts it in the buffers for us. So now it's also important to realize that a receive involves software on the remote side. So it's not completely hardware driven like the RDMA semantics are. But let's look at the same problem that we had before. I have more messages that I want to send than I have buffers available. So what exactly happens here? Well, nominally the same thing happens. You have to wait for one of the messages to be consumed by the receiver such that that buffer becomes available and can be posted on the end, and then message 4 can be sent. But who decides? Well, I have a little footnote there, or it might R&R. Let me explain that there. Either Open MPI has to decide and do its own flow control and say, oh, okay, well, I know that there's not enough buffers, so I'll wait, and when I get enough acknowledgments, I'll send it. And there's certain cases where Open MPI can do that, but in this case here, where there's a shared set of receive queue buffers, there's no way for any sender to know whether there are enough receive buffers or not. So in this case, Open MPI will generate a network level event called an RNR, a receiver not ready, that the receiver will actually send back a packet saying, sorry, I have no buffers, you need to try again later. So Open MPI will delay a little bit, the sender will delay, and then message 4 will be retransmit. And when there is a buffer available, it'll actually finally get through. So this is good from a memory performance standpoint, but it can be bad from an actual network throughput performance standpoint. It's trade-offs. So let's look at a little more objective classification here and comparison of RDMA versus send. So as we discussed, buffers need to be set up for each peer on an n-by-n basis for RDMA, right? So number of peers times number of buffers per peer, that's how much registered memory you need to consume ahead of time. And you have to do this initial handshake of exchanging all the addresses. Now MPI maintains all the accounting and flow control too. So it has to know, oh, there's only 3 buffers, I've got 4 messages, I have to wait for the ACK to come back and say that a buffer's free and do all this kind of stuff. Now here's something I didn't mention on the previous slide, is that when you're doing RDMA and it's completely hardware driven, there's nothing that goes up in the software stack that says, hey, a new message has arrived. So MPI actually has to go poll memory locations and say, hey, did something arrive here? Oh, there's a new message here, now I need to process it. So MPI is responsible for noticing that new messages have arrived. RDMA is also unordered, which really doesn't matter too much in this case, but it is nice that it's a truly one-sided operation, completely driven by the hardware. So in general, it's a little more work for MPI. Now on the send-receive side of things, we do have to set up a pool of buffers, but it can be less than n by n, and we'll talk about that several slides from now. So you can actually save a little bit of registered memory, and that can be pretty important, especially at scale. Now, the network driver and hardware maintain some level of accounting and flow control. In some cases, OpenMPI can do its own flow control when it's not sharing receive buffers, but when it's sharing receive buffers like that, there's really no good way, and we have to fall back to the network hardware level flow control. Now, again, something analogous to what I said for the RDMA, on the send-receive side, the network does notify us when new messages come in. We get a little event in OpenMPI from the OpenFabrics verb stack that says, hey, a new message has arrived, here you go. So we don't have to go poll a bunch of different memory locations. We can just poll one location and all messages come in through there. Data that comes in through the send-receive side is ordered, and it is two-sided. So it does involve the software stack on the other side, so it is slightly slower. But it is a little less work for MPI this way. Now, we said before that doing the short message RDMA is unscalable. However, it's faster. And since MPI is judged very much on 0 and 1 byte latency, we have to do optimization tricks to make sure that our 0 and 1 byte latency is as fast as it possibly can. And that means using RDMA, even though it's not scalable. So one of the tricks that we do is we just limit how many peers are allowed to use short message RDMA. So what we do is we say the first N peers that contacts me says, all right, you guys can use RDMA for short messages because you're my super close friends, and I'll dedicate some network RDMA buffers for you, and we'll be nice and fast talking to each other. The N+1th peer will fall back to using send receive for short messages. Basically, it's the receiver's choice. He says, the receiver blesses a sender and says, hey, you can use RDMA, or no, I'm sorry, you must fall back to send receive. So basically, if M buffers are posted for each RDMA peer, then the total registered memory so far is M times N times the short message size. All right, let's talk about another concept here there's two kinds of receive queues in the OpenFabrics verbs. There's per-peer receive queues and there's shared receive queues. So in per-peer resources, Open MPI can do its own flow control because there's only one sender and he knows how many buffers are in the receive queue on the other side. So he knows when the queue is full and when he needs to stop sending and wait for ACKs and things like that. So we never error in this situation. In pooled resources or shared receive queues, there's no flow control because there's so many buffers, but there's more than one sender, so it's not possible for any given sender to know when all the buffers have been exhausted. Now, you can get better utilization of memory this way, but you're kind of playing the stats game here, and you have the potential for retransmits. So it really is a trade-off, like I said before. Better memory utilization, potentially worse network performance. So if you look on the right is kind of pictures of what both of them look like. On the per-peer receive queues in the top right there, you can see for each of the 4 peers, they have their own queues. The yellow boxes represent buffers, and the gray boxes represent memories or messages consuming those buffers. So you can see peer 2 is actually blocked from sending any more because his queue is full. However, down in the lower right-hand corner, we have a shared receive queue, and I have the same total number of gray boxes in there, but peer 2 is not blocked anymore. There's a lot more buffers that peer 2 could use to keep sending before an R would occur. So better performance that way because there's more buffers to consume, but if the shared receive queue ever does get full, if the receiver becomes slow and stops consuming, then you get network retransmits. Again, trade-offs. Now, a nice thing about the shared receive queue is we can say, well, now wait a minute. If in the previous picture there, I had exactly the same number of buffers as I did for per-peer receive queues. So really, what was the point of using a shared receive queue? Well, the point is you can get away with less than n by m buffers. You can play a statistics game, like I said, and say, all right, well, I know that my application is not too bursty, and I can know that what the total number of outstanding messages is going to be. So let's post something less than n by n buffers, and I'll have more memory available for my application to use. And I can say, all right, well, just by the way my application behaves, I know that I'll never fill up the SRQ and cause RNRs. Or even if I do cause RNRs, it's not enough to completely impact performance. Now, that's pretty much how we do short messages. How do we do long messages? Well, long messages are a bit more complicated, believe it or not. We have a pipeline protocol, which I'll go through and I'll show in the next couple of slides here. We basically fragment the message and have an event-driven queue, and it loops basically over this, that we register the memory for the fragment, then we either send or receive it, and then we unregister it. Now, I'm skipping a lot of details here, there's actually a paper on the Open MPI website that describes this in a lot more detail. And the protocol is actually even a bit more complicated if the message is not contiguous. And I'm not really going to describe that here. You can kind of extrapolate that if you want. But generally, this is what happens for a contiguous long message. Let's have a look at it pictorially. So I do an MPI send of a long message, and that blue buffer, or that blue box there, represents the buffer. And we have 3 phases. So we have eager and match data as the first phase. And then we do a couple of send receives, and then we do RDMA for the rest of it. So let's see how this breaks down here. The phase 1 is where we find the receiver match. Now, the goal here is that we don't want senders to overwhelm a receiver. So let's say I'm sending a 10 megabyte message. I don't want to send the 10 megabyte message until I know that the receiver is able to receive it, has a buffer to receive it in there. Because otherwise I could just run the receiver out of memory before they ever even get into MPI. So what I do is I send the first fragment along with the match information, like the communicator and the tag and things like that. And I just use regular send-receive semantics, and I send it over to the receiver. Just a little bit of data. And there's a rendezvous. This is a very typical rendezvous kind of protocol. We certainly didn't invent this, but we're utilizing it here. So when the receiver finally gets around and says, oh, yes, I have a receive that is posted that matches that, then we go into phase 2. In phase 2, the receiver is starting to register the buffers to receive the rest of the message, and that takes a little bit of time. So what we do to hide that is we start using send-receive semantics into pre-registered buffers on the sender, right? So we send a few more fragments, these green phase 2 fragments, to cover up the latency while the receiver is preparing to receive the rest of the message. And we do have pipeline protocols, and it's subject to a max depth setting, and you can do some nice tricks about conserving your resources and whatnot. But the gist of it is that once the send-receive phases there, the send-receive fragments in phase 2 are done, then we go into phase 3, and we do use RDMA for the rest of it, which is hopefully the bulk of the message there. Again, this is a long enough message that having these 3 phases in this pipeline protocol actually pays off. So what we do is we kind of pipeline, we register each blue chunk, and then we write it, and then when that blue chunk is finished writing, then we unregister it. And you can see as time goes through here, and again, I'm avoiding a whole lot of details, but we kind of pipeline the registers and writes, and then eventually the writes will complete and we unregister them. And at the end, at the very bottom right of the picture, when the last fragment is done, we unregister it, and then the entire message is complete. Now, the obvious question is, why on earth are we doing something so complex? Why don't we just register the whole darn buffer, do a single RDMA write, and then a single unregister and be done with the whole darn thing? Well, the answer is that the time taken to register and unregister the buffer is directly proportional to the length of the buffer. So if you register one whole long buffer and then send it, you can't start sending until the entire buffer has been registered. So our pipeline protocol just registers a little bit and then allows us to send immediately. So basically we're getting a jump on the latency for long messages here, that we don't have to wait for the entire long registration before sending. We can start sending much, much earlier. And as a matter of fact, basically the easy way to think about it is that the total time is longer to do it that way. Again, I skipped many, many details on the pipeline protocol here. There is a paper on the website that describes it in much more detail. Let's talk about a few other issues here. Fork support. So fork and registered memory are problematic in Linux. You must differentiate between the parent and child registered memory. And I'm not enough of a kernel guy to explain this properly, and if I did, I would get it wrong. So I will just say that it's problematic. It's not properly supported until these versions, OFED version 1.2, Open MPI 1.2.1, and kernel 2.6.16 or later, although some Linux distros have backported this. So for example, Red Hat 4 Update 6 is a 2.6.9 kernel, but they have the right stuff in there to make this work. Now, when fork is supported, it's still problematic, shall we say. You can fork, but I would advise the only thing you really do is exec after that. Don't try and touch memory that's may still be in the parent as well. There's issues. I'm not really going to go into the details here. Suffice it to say that calling system should be okay, or fork immediately followed by exec, but don't try and be much more clever than that. There is an MCA parameter that will tell you if Open MPI was built with the proper fork support. It doesn't tell you if your system supports it, but it tells you if Open MPI supports it. It's this BTL OpenIB have fork support. You can use Open or OMPI info to query and see what the value is for your installation. Another random topic here is striping. Striping large messages and striping short messages. When does Open MPI do this? Well, short messages are round robin cycled or round robin across the lowest latency BTL. So the lowest latency network that you have in your OpenMPI program. So let's say you have a dual port HCA on an InfiniBand network. OpenMPI, assuming that those are both the same speed ports, OpenMPI will round robin short fragments across those. Long messages are automatically the fragments. Remember how we split up long messages? We automatically round robin the fragments in large messages, so we automatically stripe across multiple OpenFabrics devices there. Now, the size of the long message fragments are actually directly proportional to the network capacity. So, for example, InfiniBand has a nice property that it reports up what its actual bandwidth is. And OpenMPI, let's say you have an SDR port and a DDR port, OpenMPI will do the right thing and send more data down DDR than it does SDR. We developers are investigating more complex scheduling scenarios, but for the moment, that's what OpenMPI does. So how exactly do you activate striping? Well, you don't do anything. You just run. MPI run, your application. If OpenMPI detects multiple OpenFabrics ports, it'll just use them all. And that's assuming that each peer port is reachable to each other. And that's determined by the subnet ID. So let's have a look about this here. This is particularly an InfiniBand issue here. The subnet ID uniquely identifies an InfiniBand network. So all Cisco InfiniBand switches, and as a matter of fact, I think most if not all InfiniBand switches ship with the default subnet ID of FE80 followed by all zeros. So if you're going to have multiple physically disparate InfiniBand networks, you must have different subnet IDs on here. So this is an Open MPI restriction. It's not an InfiniBand restriction. It's an Open MPI thing so that we can compute reachability properly. But still, ambiguities exist. So let's look at this pictorially here. Let's start in the top left corner here. You can see I have two switches, and the switches are not connected together. But I have 3 HCAs. So you can see the connection pattern there. It's a little non-uniform and kind of contrived for this slide here. But let's look at it here. So on switch 1, I have a subnet ID of ABCD. And on 2, it's EFGH. This is good. OpenMPI can properly compute reachability in this scenario. Now let's look at the top right here. I have the same connection pattern, the same switch pattern and whatnot, but it's bad because both switch 1 and switch 2 have the same subnet ID, ABCD and ABCD. So in this case, for example, OpenMPI could erroneously conclude that the second HCA can reach the third HCA, and that's not true. It's incorrect. There is no network path between the second and third one. So OpenMPI would either hang or crash in this situation. Now in the third scenario at the bottom, this is actually slightly worse. It's almost the same as the top right one. I have the same connection pattern, but they both have the default subnet ID, FE80. So OpenMPI number can't compute the reachability, and it will also warn because it'll say, you know, I see multiple ports out there, and they have the default subnet ID. So I don't know if that's actually you intended it that way, or you just have a bunch of switches that you haven't configured yet. So I'm going to print out a warning message. There is actually a way to turn off that warning message if that is the setup that you desired. So let's say those two switches were connected to each other. That would be a perfectly valid network configuration, and you wouldn't want OpenMPI to warn in that situation. But just to make you aware of this scenario, that it exists, and OpenMPI needs to be able to compute its reachability properly. I've thrown a whole bunch of information at you. There's a bunch more on the OpenMPI FAQ on our website. Go into the two categories. One is for general tuning, and another one is for OpenFabrics tuning, and there's a lot more information there. That's all I really wanted to say today. I hope this information was useful to you. Thanks.